All right. So after that introduction to random processes, we'll kind of take use of that fact that we have that background, and we're going to go back to something that we saw a while ago and that you guys are working on in this current homework exercise, and that is the rate chaos in asymmetric networks. Okay, so let's all remind ourselves the model we're talking about. We have tau h dot I is minus hi plus the sum over j, jij, and then we have this transfer function g of hj. Okay? We defined the matrix jij to be totally IID independent Gaussians. Jij normally distributed with mean 0 and variance j tilde squared divided by n. That scaling of 1 over n in the variance was important. And then we have g, the transfer function, is the hyperbolic tangent with a beta parameter. Okay? And what we saw previously was that for j tilde beta smaller than 1, we have a stable fixed point at 0. That is, all neurons equal to 0. This is a stable fixed point. And for j beta greater than 1, we lose stability. And we observe chaos, rate chaos. Okay. So what I want to do today is use the background that we've already established on stochastic processes to go back to the analytical solution of this model, and also use that as an opportunity to introduce a few more things about stochastic processes. So the approach that we use to solving the statistics of this model is called dynamic mean field. And what we're going to do, as I kind of described partially a few weeks ago or a month ago or whenever it was, is that we are going to study the statistics of a typical neuron in the network. So we're going to think about the statistically typical neuron hi as kind of disjoint from the network. And then over here we have this whole cloud of a network, kind of make it look cloudy. And the neuron is drawing its input from this network. We're going to make a crucial assumption that the activity of each neuron is independent, uncorrelated from the activity of all the others. And then this neuron is going to be summing the input from all the network. And if we can properly study the statistics of the single neuron, and then demand that it be also representative of all the neurons in the network, then we're going to look for a self-consistent solution. And so specifically, we're going to write eta I, the input, into neuron I, which is just our sum over jij g of hj, from j equals 1 to n. Right? And if we're assuming we're treating this whole problem as hij is itself a stochastic process. So if all of these h's in the cloud, in the network, are random variables, and then we look at this sum, this input into the neuron is also a random variable, and in particular in the limit of large n, the central limit theorem tells us that this is a Gaussian random variable. The input into the neuron at any given point in time is a Gaussian random variable. So in the n goes to infinity limit, eta I of t is a Gaussian random variable. Okay, and so that gives us a segue to introduce continuously indexed Gaussian random variables. So this is an extension basically on what Jonathan was talking about in terms of stochastic processes. Now we'll be talking about Gaussian stochastic processes in particular. So for this hour, I'll kind of step away from our dynamical model and the network and just talk about Gaussian processes. Yeah, dynamic mean field is the analytical approach to solving this model and other similar models. And at least as far as I know, always makes use of the statistics of Gaussian processes. So now we'll take a step back and just look at and introduce Gaussian processes. Okay, so a Gaussian process is a particular form of a stochastic process in which basically just all the points in time are Gaussians. So the white noise process, in the way that Jonathan introduced it, was a particular example of that, although just to point out, white noise doesn't have to be Gaussian. Usually it's assumed that it is, but it doesn't have to be. And Gaussian processes are generally not white noise processes. Only the white noise is a specific case. So generally speaking, a Gaussian process, write the definition, is a continuous stochastic process in which all finite sets of points have a joint Gaussian distribution. So they're jointly Gaussian distributed. Right? That means if we take any set of points, y of t for different points, tk, right, I'll call my Gaussian process y of t. That's what I'm going to call it for now. For some set of points, Q1, some number of points, they have some joint Gaussian distribution. And in particular, we also know any joint Gaussian distribution, so all the marginal distributions are Gaussians. So the marginal distributions, just the distribution, the effective distributions on single time points, y of t0, are also Gaussian. Okay. The powerful thing about Gaussians generally, the reason we like them so much, is that they're entirely determined by just the first two moments. Once you have the mean and the covariance of a set of joint Gaussians, so that determines the entire probability distribution. Or you can write fully the probability distribution, the probability of any possible values of those variables.
What are
Marginal distributions are distributions in just a single random variable. So generally, when you have a joint distribution of random variables, when you take the marginal, you're basically integrating over all the other variables, putting them aside and ignoring them, and saying what's the probability of this one. In this case, we're talking about the marginals of single time points. So the probability of getting a value just at some single time point, independent of all the others. of all the other times. Right. Okay, so Gaussians generally, we know, are determined by their mean and their covariance. So that's true also for a Gaussian process, that it's generally determined, fully determined by a mean function and covariance function. A mean function and covariance function. Which is, I guess, Jonathan was calling the correlation function, covariance function, C of t, t prime that Jonathan talked about. So if we know the mean function and the covariance function, we know the entire probability distribution of all time points. Yeah.
Can you repeat what's the covariance function? How do you describe the process?
Yeah. So the mean function is simple. It's just an arbitrary function of time that tells you the mean value of the function at that given point in time. And the covariance, so we saw it in the first hour, but I'll write it again formally. So C of t, t prime in the general setting, right, is the average of y, the random variable at time t, minus the mean at that time, times y at time t prime minus the mean at that time. So that's the general formal definition of the covariance function or correlation, autocorrelation function, whatever we call it. Okay. But now, so like Jonathan said, normally we study the situation in which a few things. So first of all, we most commonly will write the mean function, take the mean function to just actually be 0. Because what you can always do is have a deterministic function of time and then add on top of that the random part with the noise. So we'll take in our setting y of t equal to 0 as the mean function. Yes. Generally, it could be dependent on time. Now, the next thing I'm going to say is that we're going to be studying stationary distributions, and in that case, in a stationary distribution, which Jonathan mentioned in the first hour, so in that case, the mean will not be dependent on time, and also the covariance function also won't be dependent on absolute time.
The bar over bar means average over sample. The triangular bracket is over time.
For now, the bracket is also, for now, an ensemble average. I'll talk about that also. We're going to assume ergodicity, which Jonathan mentioned. So let me keep laying out in our particular setting. So we'll assume the mean function is uniformly 0. I use the bar just as a notation, not to mean that I'm taking any kind of average. I'm just saying I'm defining some function, which will be the mean, which will be the average. And then we'll just take it to be 0. That's common because, like I said, you can always, if there is a non-zero mean, you can take that to be a deterministic function that's unrelated to the Gaussian process, and then add the random part, which has 0 mean. So we'll assume that it's 0 mean, and then also we'll assume a few more things. One, that it's stationary. Right? So stationary means that C of t prime, which in principle could depend on both time points, only depends on the time difference. Right? T minus t prime. And formally, so Jonathan didn't get into this level of detail in the definitions, but just this is how it's often in the literature. This is stationarity, and then homogeneous is another property, which means that not only does it only depend on the time lapse, it doesn't depend on the order of the time lapse. So in that case, C of t minus t prime is equal to C of the absolute value, T of T prime. So it's kind of symmetric with respect to the order of time. Okay, and so in that case, and I'm going to use notation a little bit different than Jonathan's. I hope it doesn't confuse you. So in that case, we can write C of tau. Tau is going to be the time difference, and that's going to be defined as just the average of y at time t times the average of y of t plus tau. And in this case, it's going to be symmetric, so we could take t as plus tau and t minus tau, and by our assumption of the structure, it's going to be equivalent. So that doesn't matter. And the last thing we're going to assume is now about Yoav's last question about the meaning of this angle bracket. Formally, what we mean when we write the angle bracket is we're taking an ensemble average, meaning, like Jonathan said, we run the Gaussian process all the way through, and then do it again and again and again, and take the average for every time point. But we have this additional assumption of ergodicity, of ergodic. And that means that basically the random process samples its own probability distribution over time fully, such that taking the ensemble average is identical to taking long time averages. So that means that anytime we take any average of the random process, I'll put in some arbitrary function g of y of t, and it could be also, and this would hold for higher moments, that's going to be equivalent to taking the limit of t goes to infinity, and I'll write it as 1 over 2t, taking the integral from minus t to positive t of dt, and then that same function that we're interested in taking the average of g of y of t. So that ergodicity just means that we ignore we're able to ignore the difference between taking an ensemble average and taking a time average, that they're effectively guaranteed to be the same, at least in the limit of long time. Okay? That's most commonly the situation when people study Gaussian processes. Any questions? No, that's an interesting point, right? There's no probability played in. Basically, we assume that the random process is sampling its probability distribution just as it runs over time. That's a good conceptual question. And so, just by running itself over time, it's sampling all the possible points and then giving us all the moments and all the means and all the statistics that we could be possibly interested in averaging. Okay. And when we saw one extreme case, we saw the extreme case of this in white noise, where C of tau has a delta function, and all discrete points in time are independent from one another. But generally, C of tau can have any form that it wants. Okay. Okay. So now I'll introduce a couple more definitions or measures that are commonly used in the study of random processes. That's energy and power, and also their spectra. Okay. So the energy of a signal or a random process is the integral over all time of the signal squared, simply the squared signal or the squared random process over all time, integrated over all time. And now, what is commonly done, and we'll kind of see why this is done, is in the study of random processes, we use the Fourier transform quite a lot. So just to remind you of the definition, we take the Fourier transform of a signal, of a function, generally. You can call it y hat, and it's a function of omega, right? And it's the integral minus infinity to infinity, integral over time of the function times e to the minus I omega t. And that's one convention. There's different conventions with regard to the sign and with regard to the normalization. We'll actually see another convention kind of in a moment. Okay, and one thing that we're commonly interested in terms of random processes, and again we'll see more why it's of interest, is we're interested in taking a look at this energy and seeing how it's distributed over different frequencies. So that means we think about our random process fluctuating randomly in time being decomposed into sub-signals, sub-processes that have different frequencies, different cosine terms, and we see how much of the total energy is distributed to each of the different frequencies. So in particular, the energy spectra, we could write as E as a function of omega, as just the norm squared of the Fourier transform for a given frequency, omega. All right, so generally the Fourier transform gives us a complex number for each frequency omega, and that tells us the norm for that frequency and also the phase. And here we're saying we don't care about the phase, we just care about the norm, basically the norm squared for that phase. And we know, so this is the energy spectral density. Spectral density. And one of the powerful features of the Fourier transform is that we can, just like we wrote the energy as the integral over all time, we can also write the energy as the integral over all frequencies, and it's totally equal. I think that's called Parseval's theorem. So these two are equal. That's a property of the Fourier transform because the Fourier transform is kind of using an orthogonal basis. So that basically both of these are like the norm squared of the vector, and it's invariant to transformations by an orthogonal basis. You want the linear algebra kind of frame on that. Now this energy is oftentimes infinite, because we're integrating over infinite time, so unless we have particular bounds on the function, it might be infinite. So oftentimes, what we do is we study instead what's called the power. You can normalize the Fourier by the square root of 2 pi, but you can leave it this way, and then when you do the inverse.
Yeah, but for Parseval's theorem, it changes, normalizes.
You have to make sure you're doing the normalization, that you define the normalization right on the return. You're technically right. I'm assuming we normalize everything correctly. Yeah. We'll look at the power. So like I said, the energy can be infinite. So what we often will do is just look at the energy per time. So instead of the full integral over time, we take one of the limit, again. The limit of t goes to infinity, and 1 over 2t. So we're just normalizing by time of the exact same thing, y of t squared. So that's the power per time of a signal or of a random process. Okay. And now we know we want to do something comparable to distributing the energy. Like we did here, we distribute the energy per different frequency, so we want to do the same thing with the power. We want the power spectral density. And for this, we kind of have to define a differently normalized Fourier transform that effectively kind of carries forward this time average into the Fourier domain. So what we can do, I'll call it y double hat as just a different normalization. Don't worry about this too much, but I think this is the technically right way to to define this is if we define this normalized, time normalized Fourier transform, we put in a limit as t goes to infinity and 1 over the square root of 2t minus t to t, and otherwise it's the same Fourier transform. Y of t and then e to the minus I omega t. So now we define the power spectrum, or the power spectral density, commonly called S, and then it has this funny notation for some reason, with the subscript being the function written twice for some reason. That's how I saw it on Wikipedia. And that's just simply this normalized Fourier transform, the norm of that squared. So this is the power spectral density. Spectral density. Okay, and that's super commonly used in signal processing and also in the study of random processes. We'll see in one moment why that is. And just to point out, in our setting, we're talking about real signals, real functions, or real random processes that are always real. So in that case, we know that that y of omega, we know that y of omega is equal to the complex conjugate of y of negative omega. So we know that this is equal to y double hat of omega times y double hat of minus omega. Right, again, because we're guaranteed for real functions, the Fourier transform of minus omega is the complex conjugate of y of omega. Okay, so that's a lot of background kind of equipment. And now, why is that important for random processes, in particular Gaussian random processes? So,
power spectral density gives me an intuition in every frequency how much I have signal compared to noise.
Here kind of we're only talking about noise. The signal is noise, but you're right. It tells us at every frequency how much noise I have, how much power I have at each different frequencies. If we're dominating by slow oscillations, or if we have a lot of high frequency noise.
It's not describing the signal noise ratio.
Right. Here we have no signal to noise. We're looking at basically the properties of noise, different noise signals. Noise signals, right? Not signal and noise. Okay. Okay. So the reason this is important is because of an important fact about the covariance function, the correlation function. So we have an important fact about C of tau. Okay. So the important fact about C of tau is basically its Fourier transform. So it turns out the Fourier transform, we said we've defined our entire Gaussian process basically is fully defined by C of tau in our particular case where we have mean 0 and everything. So C of tau is fully determining the random process that we're talking about. And it turns out that the Fourier transform of C of tau is exactly the power spectral density. So that's why this really becomes such an important quantity. So let's see that. So we'll take the Fourier transform of C of tau. Okay? So we have integral. Now, notice we have an integral d tau, because C is a function of tau, the time lapse. And we have here, C of tau is the average, ensemble average, or time average of y of t plus tau. And then e to the minus I omega tau. Okay, so now I'll plug in, instead of the ensemble average, we'll really make use of the ergodic property of our random process, and we'll write in here that the ensemble average is replaced by the limit of t going to infinity, 1 over 2t minus t to t. Now we're taking an integral over the time t, y of t plus tau. Okay, so we'll put that in place of the ensemble average, and then we're going to switch the order of integration. So we're going to get that our Fourier transform is equal to, we put out here the limit t going to infinity, 1 over 2t, integral to minus t to t of dt, and now the integral over d tau. Y of t plus tau, e to the minus I omega tau. Okay. Now, this term y of t is independent of tau, so we're going to be moving it to the other side, and it's only going to be affected by this integral. And then these terms, we're going to take the integral over tau. But we can do a useful change of variables first. We'll write t prime is equal to t plus tau, so that d tau prime is just the same as d tau. And then we're going to switch and make y a function of t prime. And over here in the exponent, we're going to write e to the minus I omega tau prime, e to the positive I omega t. Right? Let's just switching tau is equal to tau prime minus t. And that's going to allow us to totally separate our integrals, because now we have y, a function of t, is just going to be in this integral. Y, a function of tau prime, is just going to be in this integral. E to the minus I omega tau prime in this integral, and e to the I omega t only in this integral. Right? So I'll write that out. And what I'm also going to do is already separate out 1 over 2t into the square root. So I'm going to distribute that. I'm going to write 1 over the square root of 2t for the first integral, dt, which has y of t, e to the positive I omega t. And then another 1 over square root of 2t, integral from minus t to t. Now it's d tau prime, y of tau prime, and e to the minus I omega tau prime. And that's already very nice, because that's exactly this kind of time-normalized Fourier transform that we wrote, that we defined over here. And we're just doing it once in the normal form of the Fourier transform, and once here with basically a minus omega, so that we get a final result. The Fourier transform is equal to y double hat, this time-normalized, of minus omega times y double hat of positive omega. And like we said, because we have a real signal, that's equal to the norm squared, y of omega absolute value squared, which is just our power spectral density. Okay? Any questions about that process? So what we've shown is that the correlation function c of tau, which fully determines our Gaussian process, its Fourier transform is the power spectrum. So those are formally equivalent. So if I give you the power spectrum of the Gaussian process, that also fully determines the full statistics of that process. So I kind of want to keep this board. So let's try to get a bit of an intuition for what that means. So that means it's totally equivalent to look in the time domain or in the frequency domain of a Gaussian process, and we can fully determine the statistics from either perspective. So let's look at an example, and we'll use the example that Jonathan worked with in the first hour, which is the white noise. So we'll look at a particular case of Gaussian white noise. And in that case, C of tau is equal to, in Jonathan's notation, sigma squared tau core, and then a delta function, delta of tau. Okay. So what's the power spectrum of Gaussian white noise? S of omega is just the Fourier transform, d tau, sigma squared tau core, delta tau, e to the minus I omega tau. Okay, the delta function only means that this integral only gives us a value for tau equals 0, and then it gives us a value e to the minus I omega 0, which is 1 from the exponent. And that means the entire integral is equal to sigma squared tau correlation. So the power spectrum of a Gaussian random variable, the spectral density, is constant, right? So this function of omega is constant, it's flat. And that's really why it's called white noise, just kind of like brought in as a metaphor from light, where white light has all the different frequencies of light. So that term was borrowed into noise and random processes because of this property, because the power spectral density is constant for all frequencies. Okay, so now let me try to give you a schematic of those two domains that you can look at the random variables of Gaussian processes in. So we have the time domain and the frequency domain. Right, so in the time domain, we're going to draw C of tau, the correlation as a function of the time lapse. In the frequency domain, we'll draw the spectral density, S of omega, which again is the norm squared of basically the Fourier transform, and it's the distribution of power to different frequencies. So on one extreme side, we had the case where we have the delta function. So in this case, formally, mathematically, in the limit, we only have C of tau, sigma squared tau C delta is infinity at the point 0. That's in our time domain. And in the frequency domain, we said S of omega is constant. Not a function of frequency at all, so it's just flat. Okay? Let's look at the far side over here. Suppose that we had C of tau constant. Now, in the way I set things up here, that would have to, the only constant it could be is 0. But well, for the sake of this example, I'm going to just change our definition and assume, and instead of talking about C of tau, we're going to talk about an example of a case of a random process that has non-zero mean, and we'll talk about y of t plus tau without subtracting the mean, just for the sake of example, in which case we can have a C of tau that's constant. That just means the function itself is totally constant. It's flat. There's actually no noise. And in this case, what do we find? If we do a Fourier transform of a totally flat, constant function to look in the frequency domain, so we find the only frequency component that contributes is the 0th frequency component. That's the mean. That's what's called the DC component. So the Fourier transform of this kind of signal is just a delta function. We would have S of omega proportional to some delta function with omega at 0, delta of omega at 0. So these are extreme cases. And in between, let me just give you schematic drawings. We could have a narrow C of t, relatively small temporal correlations. And if we were to do the Fourier transform and look at the power spectrum, in that case we'll have a kind of relatively broad power spectrum. If we have small temporal correlations and we have fast fluctuations in the signal, fast fluctuations mean we have relatively high contributions from high frequencies. Let me write the axes here. This is up here, this axis is tau, and down here we're talking about the frequency axis, omega. And then moving in the direction of the flat signal will be a signal with long correlation times, slow decay of the correlations. And in that case, when we take the Fourier transform and look at the power spectrum, we'll have a narrow distribution of the energy, and primarily low frequencies will contribute in that case. So that's kind of the schematic, rough range of Gaussian processes, random processes generally, from no time correlations, in which case the power spectrum is flat and all the power is equally distributed across all frequencies. And as you get temporal correlations being longer and longer, then you get the frequency contribution being narrower and narrower around 0 until if you just have a totally flat function, then only the 0 frequency is contributing. All the power is in the DC 0 frequency component. Okay, so that's our background on Gaussian processes. And again, it's totally equivalent. You can define the Gaussian process in terms of its power spectrum by giving one of these drawings with a definition of S of omega, and that fully determines the statistics of the entire random process. And then now in the next hour, we'll see how we kind of use that to solve for the statistics of the rate chaos. Any questions about power spectral density? So just to be explicit, these two drawings could reflect what Jonathan drew at the beginning of his hour, where we had kind of this fast fluctuating signal versus a slower fluctuations as representing two different possible random processes. And so that would correspond to the narrow correlation function or the broad correlation function, and the converse is true of the power spectrum. The fast fluctuating signal has a slower decay in the power spectrum, more contribution from high frequency terms. All right. take a break. Okay, so now we're back to our dynamic model, rate chaos that emerges in this asymmetric matrix when j tilde beta is greater than 1. And what we're going to do is what's called the dynamic mean field theory approach to solving for the statistics of a typical neuron in this network. So like I said, what we've got in the limit of large n is that this eta, the net input into a single neuron, is a Gaussian process. And now we kind of learned about the statistics of Gaussian processes, right? And that means that eta I is totally determined by its correlation covariance function, which we'll write, for now, we'll write as C of tau. And we'll just assume that we have some C of tau correlation function, and that's being driven into our single neuron HI. So now from the perspective of our single neuron HI, let's write the dynamics.
So why can we assume that the mean of this is 0?
Why can we assume that the mean of this is 0? So,
I understand central limit theorem, so it's Gaussian.
right, yeah, it's a good question. So Jij, all the Jij's are drawn independently from a distribution that has mean 0, right?
Okay.
And we kind of talked about the transfer function g is symmetric, right? So that was our argument by symmetry last time, which I sort of stumbled on, but in the end kind of came around to that if we were to switch the signs of hi, of hj, of all the hj's, we would get an equivalent expression. And so we assume that it's mean 0. So let's write the mean field dynamics. We have tau. I'm going to call tau h to differentiate it from the tau in the time lapse in the definition of our correlation function. So we have tau h of hi. Now thinking of it in terms of the typical neuron, it's minus hi. And all this input from the network, we're just going to write it as eta I of t. Right? So we've reduced our entire problem, which is a highly recurrent network where there's a nonlinear transfer function. And we've now written it as just a single variable, and it's a linear dynamical equation, right? There's no nonlinearity here, with some noise term. With eta I of t on average equals 0, and we have this correlation term, C of tau. And now C of tau fully determines the statistics of the noise, because it's Gaussian in this large n limit. Okay, now let's look, what about the statistics of HI? So that's what we're going to be interested in, the statistics of HI. So this is just a linear differential equation now. So what's the solution? Who can tell me? Jonathan did one of these last 2 hours ago for the case of a membrane potential.
It's HI 0.
Yeah, well, let's just already ignore the initial condition term. We'll do just like Jonathan did and wait long enough time for the initial condition to decay. So then what's that next term?
And tau divided by r, I think.
The other way around, 1 over tau. And then we have that integral, right?
Yeah.
The integral goes from time 0 until the current time t. And then we have ds integrating over all past time. The exponential kernel, which is minus current time minus any given past time, divided by tau h. And just the value of eta at time s. So for a given instantiation of the noise, if we know a full form of eta, of the input, then we also know hi. And in particular, I just want to look at the form of it. It's an integral with different weightings of this form, right? So an integral is basically just a sum, right? And this is a Gaussian random variable, so we're just summing over a Gaussian random variable. And so we know the sum of a Gaussian random variable is also a Gaussian random variable. So then we know HI is Gaussian, which is great. That's great because its entire statistics is determined by its mean and its correlation function. And just like in the case that Jonathan did, the mean of HI is also going to be 0 just because the mean of eta I is 0. And so that means that the full statistics of HI will be given if we can calculate the autocorrelation. So all we need is what we define, like I did last time I talked about this, call it delta, which is just the autocorrelation of HI, the correlation function as a function of tau. So that's all we want. And what do I mean that's all we want? I mean, we want to find delta, but we need to find it in a way that's going to be self-consistent with C of tau, because at the end of the day, delta defines the statistics of these HJs in the whole network, and those determine the statistics of the input eta. So we are going to have to close the loop and require self-consistency at the end. Okay. So how do we find the autocorrelation of HI? Well, we could kind of do like Jonathan did. Jonathan basically did this for the membrane potential, right? He had the same basic expression for the membrane potential, and he asked what's the correlation function of the membrane function, and he did two integrals. But I want to introduce a kind of quicker way to do it, which is, again, going to the Fourier domain. But now it's the Fourier of the dynamics. Okay, and we're gonna make use of, first, what we need is the Fourier, the Fourier of the derivative, of the temporal derivative of a function, which some of you guys may know. I think I did it in a bonus hour, but I'll do it again here. And so first we're gonna need the inverse Fourier transform. So h of t, let's drop the I for now. H of t is equal to the inverse Fourier transform of, and I'm going to use, just sort of conceptually doesn't matter, but just kind of technically matters. I'm going to use the time averaged form of the Fourier transform that I used when I defined the power spectrum. So we're going to want to write h of t as the inverse of the time average form of the Fourier. And so that means we're going to write the limit as t goes to infinity. And here, because we're using the form of the Fourier transform that had the 1 over 2t, square root of 2t. In this case, we have square root of 2t. And we'll also need 1 over 2 pi for the normalization, I think. But the point is really not the normalization. What I'm going to use here is now I want to know about the time derivative of h, and I'll do it in a general form. Any given time derivative, the nth time derivative of h, dtn, and I'm going to use this form of the inverse Fourier transform because in this case the time derivative can go in. It only affects the exponent here. So when I do the time derivative on this form of h using the inverse, Everything else stays the same, assuming I did it right. Or even if I did it wrong, it stays the same. This is the double hat. And then we just have the time derivative of e to the I omega t. We have the nth time derivative of e to the I omega t. Right? What's the nth derivative of e to the I omega t? Each time derivative of e I omega t brings down I omega. Right? So that just gives us I omega to the nth power, e to the I omega t. So the full expression, keeping all the other terms around, square root of 2t, 1 over 2 pi, t to the omega, and then we have h double hat omega, I omega to the n, e to the I omega t. Now what we want is the Fourier transform of this time derivative. So because all we have here is the inverse Fourier transform of this function, when we perform the Fourier transform on the inverse Fourier, we just get back out the function that's inside parentheses, meaning this is our result. The nth derivative, the nth time derivative, the Fourier transform of the nth time derivative is I omega to the nth power times the Fourier transform of the original function. And that's going to be useful for doing the Fourier transform of the dynamics. Question? Okay, so let's apply that. Let's take the Fourier transform to both sides of the dynamic equation. And now we're going to get tau I omega h, assuming I'm doing the double hat form, the time averaged 1 over square root of 2t Fourier transform. Do the same thing on both sides.
Can you repeat what you're doing now?
I'm taking the Fourier transform of the dynamics of this equation here. That's tau h. Yeah. Okay, so now we can just bring h to the other side. So that's the power of doing the Fourier transform. Instead of having a time derivative, we just have I omega. We can bring h over to the other side. We have 1 plus tau h I omega, all of that, times h hat, right, is equal to n hat. Okay. Now in particular, we can take the norm squared on both sides and look at the power spectrum of each of these terms. So I'll take the norm squared. So taking this side times its complex conjugate, I'll get tau h squared omega squared, and then h hat omega squared equals the norm squared of eta, the noise term, right? And these are the power spectrum. So that's why we've done all of this, is because at the end we want to get to our autocorrelation. But like we said, the autocorrelation function is totally equivalent. It's just a Fourier transform of the power spectrum. So this is SH of omega, the power spectral density of our neuron, our typical neuron H. And this is the power spectral density of the noise. So, for example, we can write that the power spectral density of our neuron is the power spectral density of its endpoint, the noise, divided by 1 plus tau h squared omega squared. And this is the result that gives this linear equation the name of a low-pass filter. Because if we look at the input-output relationship in terms of the power spectrum, so the power spectrum of the neuron, h, relative to the power spectrum of the input, has this 1 over some constant omega squared. So larger frequencies are suppressed. I'll take a moment to point out that, for example, if we had white noise input, right, if our noise input here, eta I, was just white noise, like the example that Jonathan before, so in that case, S, the power spectrum, like we saw in the previous hour, power spectrum of the input is constant. So then we would have just S, H, H. The power spectrum of our neuron is the constant, which Jonathan was calling sigma squared tau correlation, divided by 1 plus tau squared H omega squared. So if we had white noise input, and that's really exactly the same problem that Jonathan solved in the time domain, in the frequency domain, it would be a function that looks like this, and the form of it in the frequency domain is something like that, decaying 1 over. And if we were to do the Fourier transform, the inverse Fourier transform back to the time domain, we would get exactly what Jonathan solved after doing that double integral, which was something like, it had that e to the minus tau over tau h, and then sigma squared term out front with a sigma squared over tau h, in our case, 2 tau h, I think. That would be back in the time domain. That would be the correlation function in the case of white noise. So now we can kind of try to understand what we're doing. We have this picture of our typical neuron, and we're sort of playing with the statistics of the noise to see when it's going to be consistent. So if the noise was totally uncorrelated white noise, then our neuron would give us something like this with correlations. But if the neurons have time correlations, then the noise input also will have time correlations. So that's not going to be a self-consistent solution. Right? Yeah. If we look at our typical neuron and then the cloud of input from the whole network, if we assume that the cloud of input from the network somehow was giving us white noise, totally uncorrelated with time, so we see that the result of that is to give us a neuron that has some time correlations, has this exponential decay time correlation function. But now if we look back at our cloud, this cloud is made up of just typical neurons. They're all statistically typical neurons drawn from the same statistics. So each of them would have a non-zero time correlation. And then when you sum over all of them to get the input back to the typical neuron, it also would have some kind of time correlations. So that's not going to give us a consistent solution. So the way to get a consistent solution right. So it probably would decrease the time correlations, but it wouldn't get to be fully white. But you just have to trust me on that for now. And anyway, I'm not gonna get to a full explicit solution because it's beyond our scope. But the way we get to a consistent solution is we have this equation for the power spectrum of the typical neuron as a function of the power spectrum of the noise, and we're going to take the inverse Fourier transform back into the time domain. Okay? So the inverse Fourier transform, I'll write again the equation I'm taking the inverse of. I'm going to do it from this stage here. So we have 1 plus tau h squared omega squared times sh of omega equals s eta of omega. Now I'm going to take the inverse Fourier transform on both sides. Okay, so the right side is easy. The right side, we said the power spectrum is just equal to the covariance, the correlation function. So that's going to just give us, when we take the inverse, that's going to give us c of tau, which is what we defined as our currently unknown. We don't know what c of tau is, but whatever it is, it comes up in this equation when we take the inverse Fourier transform. Now we take the inverse Fourier transform over here. So what do we have? We have 1 times s of h of omega. So that term just gives us the correlation function of h, which we call delta of tau. But now we have this tau h omega, this omega squared times s. So what we want to do is an inverse Fourier of omega squared s h of omega. Okay. So what's going to be the inverse Fourier transform of this? When we just have s, then we get back delta, the correlation function. But now we're doing an inverse Fourier on something that has omega squared times s. So it's going to give us the second derivative, exactly. We're going to use, sorry, I'm going to cover that up for a second. We're going to use what we used earlier. Now we see why I did this in general. In the general form, we took already the Fourier transform of all time derivatives, and we found that we got I omega n times the Fourier of whatever function we take. So in particular, if we take the Fourier transform of a second derivative of some function, whatever function it is, let's call it y, the Fourier transform of the second derivative will be I omega squared, which is just negative omega squared times the Fourier transform of that function, whatever it is. Right? So we're going to get negative omega. So now what we're doing over here is taking the inverse Fourier transform of omega squared and some function in the Fourier domain. We take the inverse transform, we just get the second derivative with a minus sign. So this is equal to minus the second derivative of that function's inverse. Back in the time domain, the second derivative, d squared of delta tau, the time derivative now is respect to tau. Okay, so let me put that into the equation. We have delta tau plus a carry forward to constant, tau h squared, and the second derivative of delta tau plus tau. Sorry, second derivative with respect to tau. Minus. Thank you. Minus. Okay. And this is almost the final form of the equation, which I just quoted to you guys last time we did this. The last thing we need to do, we also have to demand that c of tau is appropriately given by the autocorrelation function of this whole term, of this whole input. If we know the statistics of every single typical neuron H, what will be the statistics of that whole sum? We went through that last time. So I'll just write it out explicitly here. We have here eta of I at time t and eta at time t plus tau, which I'm going to write with this form, its full form, the sum over j from 1 to n, jij g of hj at some time t times the same thing, jij g at hj at some time t plus tau. And what we saw last time is, first of all, the different jij's are independent, and so those don't wind up contributing. And we can think of that as the case of that this is a sum. This is the variance of a sum. We're going to get the sum of variances. So we're going to get just the sum on j equals 1 to n jij squared. And then the statistical average of, now we have this transfer function g of hj at time t and g of hj at time t plus tau. And this is kind of the statistical ensemble average, again, because we're assuming that every single neuron is drawn from the same statistics. And this sum is really just equivalent to, for large n, it's going to be equivalent to n times the variance. N times the variance of jij. And the variance of jij we defined, and this is exactly why really we defined the scaling to be j tilde squared divided by n, because in the end our formulation is going to give us n times the variance, j tilde squared over n. So the n cancels. And if c of tau is j tilde squared, and this second correlation function with the transfer function. So this is a sum of n times the jij squared. It's n times the mean squared of j in the large n limit. That's another application of the central limit theorem. Okay, and this is really as far as I will go, but I'll say that this function is a complicated function. We have this nonlinear transfer function, the tangent hyperbolic, and then these random variables. But, right, like we said, in our limit of large n in this theory, the hj is a Gaussian random variable. So this thing is really just an expectation over two Gaussian random variables that have some joint distribution, and their joint distribution is given exactly by delta of tau, right? So this is an average over hj at time t and hj at time t plus tau, random variables that can take any possible value, but they have mean 0. They're Gaussian random variables, and they're mean 0, and their covariance is just given by delta of tau. And so that's kind of a problem that's somehow manageable. It's a Gaussian covariance. It's complicated to actually do it. You wind up introducing like a third Gaussian random variable and using fancy tricks to take the integral. But it's doable, and conceptually we can understand what it is because in this dynamic mean field theory, hj's are just Gaussian random variables. And when anything's a Gaussian random variable, then we can also take averages of functions of the Gaussian. And then what we wind up doing is we have this second order differential equation for the delta. And then also on the right hand side, eventually we have c as some kind of function that depends on delta itself. And that winds up giving us the closed loop form. And we wind up finding, we don't, but the people who did this problem wind up finding the form for delta of tau and showing that in this regime of j tilde greater than beta, the only stable solution to this equation has a delta of tau that looks something like this, which really just winds up telling us that there's some fluctuations that are non-negligible in the steady state, meaning that we have chaos, really, meaning that the system is self-propelling the fluctuations just within the network, and we have a chaotic steady state.
Can you repeat that
It really basically just tells us that we don't have a fixed point, and that we don't have oscillations, right? We kind of said when we looked at this the previous time, we kind of took a survey of the possible steady state solutions. We could have fixed points, we could have oscillations. But when we find that the only stable solution is this decaying form, so then it's neither a steady state nor oscillations, right? Because a steady state would give us some kind of flat autocorrelation function, like I mentioned, and oscillations would give us something like this that goes on and oscillates infinitely. So this decay means that if we wait long enough time, right, as a function of tau, eventually this decays to 0. That's the crucial thing, so that when we wait long enough, the system loses its memory. Right? And that's a reflection of also that sensitivity on initial conditions that we talked about in terms of the chaos, that even if we know exactly where the system is at time 0, if we wait long enough, and this curve gives us kind of a sense of what long enough winds up meaning, but we wait long enough, we can no longer predict anything about the state of the system at whatever time later. Okay? So, again, we kind of started, we have this mean field theory where crucially we assume that there's not going to be correlations between the different neurons, and then in the large N limit we can just look at a typical neuron. That typical neuron is going to be representative of the entire population, so we look for a self-consistent solution for the statistics of that single neuron, given the statistics of its input. And we use these facts about Gaussian random processes, in particular the relationship between the correlation function and the power spectral density, which are basically equivalent to one another. One is the Fourier transform of the other, and they fully determine the statistics of a Gaussian random process. We use the Fourier transform of the temporal derivative, of the time derivative, both to move from the time domain in our original dynamics, moving from the time domain into the frequency domain, where along the way we kind of saw that how the linear dynamics are also a low-pass filter, generally, and that's always the case. And then finally, we kind of saw, but didn't really fully solve because it's beyond our scope, that one can also move back from this equation to the time domain and get a second-order differential equation, which can, in principle, be solved fully to give delta of tau, and delta of tau, it gives the full statistics of the system, of the typical neuron in that chaotic system. That's it, and then I just half prepared a brief slideshow of how this chaotic system, in asymmetric networks, rate chaos, is still being studied, still has applications in computational neuroscience. Any questions? Okay, so the original paper solving this dynamics is from 1988. That Chaim Sompolinsky and Crescenti and Summers, those are the three who did it. But just to show you that it's not just history and it's still being studied. So first of all, there's been continued work in actually kind of the theoretical analytical study of these networks and doing extensions of these networks with excitatory and inhibitory neurons and into spiking models. Just last year, both David Hansel, who also is here commonly, he's a professor in Paris, and very worth getting to know. So he and Chaim both came out with a paper last year doing similar things in terms of expanding the understanding of rate chaos on the theoretical analytical tools. You can see here just plots of basically these are the delta of tau. These are the autocorrelation functions, and here it's kind of these were calculated analytically, and then simulations confirm them, and then also trying to extend these models to spiking neuron models and understand what the introduction of spiking does to the theory. But the kind of more popular, and the reason this is really still of interest, is in terms of learning. And this was kind of maybe the important article and paper that came out in that field, which is by Larry Abbott and David Cicillo in Neuron in 2009. And what they kind of used is the fact that the approach is to think about this network, which starts out as chaotic, as a kind of a reservoir. And that idea was already around in the literature, as known as like reservoir computing or echo state computing. The idea that you have some network and it has a rich kind of dynamics going on to begin with. These chaotic dynamics, so there's lots of time scales involved in the underlying dynamics of the system. And the idea is if you can train that network, the underlying networks that are there serve as a reservoir for a kind of a rich variety of possible dynamics to solve particular tasks. So they take this network and draw some random readout to begin with, a random readout from it, but then they say, I want that readout to perform some kind of task. I want to be able to drive the network with a given input or a set of inputs, and given my inputs, I want the network to be able to perform different tasks. And it turns out you can do this very successfully, and there's a number of different ways and algorithms to do it. And here's a kind of example. So you have the network start out chaotically. Spontaneous activity is this kind of chaotic rate dynamics, which you guys are seeing in your simulations. But then you say, I want the network to be able to produce this just up-down triangle shape. So you have a learning period where you're actively changing the weights to learn it to do that. And then they show here you can turn the learning off, and the network goes on doing what you wanted it to do. And there's a bunch of different examples. Here's an example with 4 inputs and 4 outputs, and it's a kind of a switch. Given a certain combination of each of these 4 outputs being on or off, you want the network 4 outputs to be on or off. And the point is kind of the complicated nonlinear tasks can be performed by these originally chaotic networks once they're trained. And it's because the dynamics to begin with are this rich reservoir of complex temporal dynamics. Okay, so that kind of sparked ongoing research to this day. But what about real brains? Does it have anything to do with them? Well, so it's sort of been suggested that maybe it does. And this paper from Bill Newsom and Mattei et al. In Nature 2013 was a paper which was based on an experimental study with monkeys performing this task. The task involves you have the monkey sees moving dots of 2 different colors, and depending on the motion of the dots, it has to move its eyes, do a saccade of its eyes to the right or to the left. But the additional thing is that there's 2 different contexts. So there's a motion. So what I said now is the motion, what's called the motion context, and that's given by the cue. So there's a cue before the trial that tells the monkey which context it's in, which part of the sensory stimulus to pay attention to. So to pay attention to the motion, the direction that the dots are moving, or the color. So if it's the motion context, it has to choose based on which direction the dots are moving. And if it's the color context, it has to choose which colored dots are more prevalent up there. If there are more green dots or more red dots. And that's kind of all the different possibilities of the directions and the different colors. And so the task has this nonlinearity because there's two different contexts, which otherwise the exact same stimulus has to produce different outputs just based on the context. So what these folks did was to build this chaotic network and train it to do the task. So you have the chaotic network, you have an input that represents the sensory evidence, motion and color, and then another set of inputs that represent what context it's in, and you train the network to just do what it's supposed to do, to solve this task properly. Depending on the motion, depending on the context, it should give a response going up to plus or minus 1, given the specific sensory input that came in. And then what they found, the interesting thing, and their claim of the interesting thing is that when they analyzed the neural data, the trajectories of the neural data while the monkey is solving this task, that actually, qualitatively speaking, the dynamics of the neural data were somewhat similar to the dynamics of the network, of the neural network model when it solves the task. And I won't get into the details because I don't so much remember, but it had to do with different axes that represent motion, color, and context, and the kind of neural trajectories given the motion and the color context, being able to kind of separate the appropriate sensory input depending on context. So those are just a couple examples. There's a lot of ongoing work. Omri Barak in the Technion has done a lot of that ongoing work too, in terms of training neural networks. And then part of the idea is, like in this example, to train the neural network and then try to analyze what's the structure of the solution that the neural networks, they call it like a black box. You have this initially chaotic network, you forced it to do a kind of complicated task, and then you look inside the black box and see what's the structure of the solution that the network came to. And the idea is maybe we can learn things about that, maybe even about the brain. Maybe. That's it. No? So? לא משנה, אוקיי. מה רצית לשאול?
אחד זה על האיבר הזה.
כן.
לא הבנתי מה זה טאו הזה של לינדר.
מה זה טאו?
כן, אם זה נובע איכשהו מזה או שזה שיקול אחר?
כן. זה בדיוק הפוריה, אם תיקח את הפוריה טרנספורמט של זה בדיוק האקספוננט. כן. כאילו, באופן כללי אחד לפי
לפי המטר הזה, לפי אומגה טאו.
טאו. כן, טאו זה הטיים דומיין, כן, אז אם תיקח 1 מינוס אומגה, אז תקבל משהו כמו חצי.
אגב, אם יש לנו בקלות את הטרנספורמט של זה, אז אפשר אולי לפתור את זה במקום להפוך את זה למשוואה דיפרנציאלית. אחת אתה לא צריך לגזור את זה, אתה צריך לעשות פשוט קונבולוציה של C של תא עם הדבר הזה.
הסיבה, לא, כאילו זה הצורה כבר חזרה בטיים דומיין.
עכשיו, אם זה טרנספורם פוריה הפוך של זה, של 1 חלקי זה,
כן.
אז אתה יכול להגיד שזה הוא הקונבולוציה של זה.
כן.
אתה צריך לפתור את זה משוואה דיפרנציאלית.
הבעיה שאתה לא יודע את זה, וגם זה יהיה תלוי יש לפי שזה זה. כן. צריך לשאול את חיים סמפולינסקי.
אוקיי.
זה, כן, כאילו שאי אפשר, למה אי אפשר ככה? כלומר, אתה יכול, אתה עושה את זה ככה, פה בצד שמאל יש לך אקספונט, זהו, אתה לא תקבל אקספוננט, כן? אתה תקבל את הבעיה שאתה מקבל את הפורי טרנספורם של איזה משהו, שאתה עדיין לא יודע אותו. כן, זה המקרה של white noise.
לא, בסדר, אבל במקרה של white noise זה הטרנספורם פוריה הפוך, פשוט.
כן. נכון. אבל זה רק במקרה של white noise באופן כללי, פה כרגע אתה לא יודע מה זה
נכון.
זה,
אבל אתה כן יודע את הטרנספורם פוריה של הפוך של 1 חלקי זה. בלי קשר לזה שזה יקבל.
כן, אז זה יהיה קונבולוציה, נכון, זה יהיה קונבולוציה בדיוק, אז תקבל פה קונבולוציה של, נכון, זה מה שאמרת, באמת, תקבל קונבולוציה של האקספוננט עם משהו שאתה לא יודע. זהו, אבל מסתבר שזה אותו דבר, כן, אז יש לך בעיה אקספוננציאלית של קונבולוציה, אבל בתכלס איך פותרים דברים כאלה, זה שהם חוזרים לדיפרנציאל equation. דווקא האינטגרל equation זה יותר קשה מאשר דיפרנציאל. אוקיי, הקונבולוציה equation זה יותר קשה. זה מה שקורה.
לא לגמרי הבנתי את זה. למה, איך הפרמטר שאנחנו יכולים להציב ב-J פיד בבטא? כאילו, בבטא נמצא פה כבר אחד מהם.
כן, אז זה ביחד, בליניאריזציה, C0, אז יש לך גם את ה-eigenvalues של זה J, שהם מסודרים באיגמול כזה עם רדיוס J תינדה, ויש לך גם את הנגזרת של G.
ששוב מקדמים ביתה יציב לפולי
בדיוק. שיש שם ביתה, ויש לך את הביתה כפול המקסימום eigenvalue של J.
זה המקסימום value, מקסימום value.
כן, זה יונתן דיבר עליו, מתי שזה לא היה שהתחלנו את זה, שכאילו, קוראים לזה Kirchhoff's law, שה-eigenvalues של המטריצה כזאת מסודרים בצורה אחידה בתוך גבול. זה אחר, שם זה משהו, זה מקרה אחר של המטריצה הסימטרית, או במטריצה לא סימטרית, אז האייגנפונקציות מורכבים, ובתוך המישור המורכב, בתוך גבול של רדיוס. אתה אמרת ש... אני לוקח
אמרת שהם מאמנים את הרשת הניבולית הקאוטית הזאת למשהו, נכון? יש כזה, איך בעצם מאמנים רשת ניבולית?
איך בפועל? אז יש כמה דרכים, כי דבר אחד, דבר שבעצם אפשר, אני לא בקיא בזה בכלל, אבל אפשר לזמן רק את ה-readout, ואז ולקחת כאילו מה-readout drive חזרה כזה פידבק, ליצור את הפידבק הזה, ואז אתה יכול חזור לקבל את הפתרון שאחר.
שכל הניבונים מקבלים את זה? אתה משתמש באוטפוט שלך כדי להכניס חזרה, ויש עוד דרכים שאתה יכול פשוט לשנות את כל ה-J, בפועל מה שעושים עכשיו, הכי מוצלח, זה סוג של דרך לחשב את כל ה-J, ב-mean gradient כאן, זה סוג של gradient descent שאתה עושה את זה איטרטיבית, נכון, מה שאתה רוצה לקבל, זה משהו מטורף שגרדיאנט לפי, עכשיו זה לפי כל J.I.J. כאילו איך שינוי של כל J.I.J. משנה לך את האוטפוט שלך, יש לי כזה, אני חושב, קרובים גם של הגרדיאנט, גם של האסים,